This video explained the second part of example, which is live load. So we are taking these examples. Now we are working on finding the live load and strength limit state design. Now first we talk about the live load. As we know, we have a H beam. If I can show that H beam here, so those are the H beam which I draw here, and each beam is 300 millimeter width. So these are 300 millimeters and 300 millimeters, and on the H beam this line is a slab, and this slab has this flat portion. So now for the case of live load where we don't have a dead load, there is no dead load, so live load is just going to applied only on this portion, which is 1400 millimeters, which we calculated. So the live load could be only on these portions for this particular beam. So if I explain this geometry, I explained this geometry on the previous in the previous video. Now in these examples we are just going to take the live load only on these portions, which is located only on this flat region. So you can say the peoples are walking on this portion, or there is a furniture moving, or there is a machinery moving. So those are considered as a live load on this portion. So that's the live load portions. Now the live load is given in the question, which is 3 kilopascals. That is given here. Live load given 3 kilopascals, and the kilopascal is basically kilonewton per meter square. So live load is given, and for this live load we are just mostly focusing on the UDL load, because there is no like in the previous case we have these triangles which is not coming into pictures, because you can imagine that we don't have anyone walking on this portion. This is this portion will not experience any live loading, so we don't have this non-uniform loading in that we experience in the live load case. So we don't have this non-uniform triangular loading, and for the live load case we just have a uniform loading. Now that uniform loading only coming from these portions. So we just need to calculate the UDL load due to the live load in kilopascal, which is pressures, times the perpendicular length, and 3 kilopascal is given, and the perpendicular length is 1.4 meters, which is 1.4 meters here. So 3 kilonewton per meter, so that is meter square, times 1.4, so that is gives 4.2 kilonewton per meter. So basically this live load has a value of 4.2 kilonewton per meter. Now that's the live load, the 4.2 kilonewtons for the B. Now the last third questions, that is asking to apply the strength limit states. So this C strength limit states. Now we are drawing again. These are the H beams, 6600 millimeter span, and we have a uniformly distributed load and triangular load. Now this uniformly distributed load consists of dead load G and live load Q, and this triangular portion, the triangular loading, only considering a dead load, not the live load. Now there is an equation for the strength limit state. So if you are checking the Australian standard AS NZS 1170.0 on page number 15, for the permanent and dead loads we can calculate that is the stability, and there is a strength in 4.2.2, where we can see that ED equal to 1.2 G plus 1.5 Q. So that is dead load and live load. Now that's the equation here, ED. So 1.2 G plus 1.5 Q, 1.2 times the dead load, which is 15.9. So that is 15.9 here that we calculated in the previous video, and then plus 1.5 plus 4.2 that we calculated just in this video, where we have calculated the live load 4.2 kilonewton per meters. So we substitute those values. We found that this has a magnitude of 25.4 kilonewton per meter. Now this portion does not have a live load, only the dead load, which is 1.2 times 19, and 19 we calculated in the previous video, non-uniform loading, 19 kilonewton per meters. So that is 19 kilonewton per meters, and that is 22.9. Now as the uniformly distributed load need to be converted into the concentric load, so that's UDL load converted into concentric load 25.4 times 6.6 divided by 2, so that is 75 kilonewton concentric load, and 22.9 times 6.6, 22.9 is coming from here, times 6.6 divided by 2, that is 75 kilonewtons. Now in the mechanics of solid, we have shear force diagram and bending moment diagram for the given loading conditions. We can draw the shear force diagram. We are interested in maximum shear force, which is W1 divided by 2 plus W1 divided by 2, which is basically the value of 167 divided by 2 plus 75 divided by 2. So this value is just 24.4 times 6.6 is equal to 167 kilonewton. So there is a small correction here, so that is 167 kilonewton. 25.4 times 6.6, that is 167 kilonewton. 167 divided by 2 plus 75, which is 75 kilonewton per 2, that is 121.2. And similarly for bending moment diagram, we can find the maximum bending moment, which is W1L over 8 plus W2L over 8. 167, we calculated 167 kilonewtons times 6.6 on 8 plus 75, we calculated 75 times 8 on 8, which is 220 kilonewton meters. So that's the final answers for the strength limit state. Thank you very much.